In this video, we're going to look at several types of ciphers and how they work. One of the first cipher types is the stream cipher. A stream cipher is a symmetric encryption method that encrypts one bit of plaintext at a time. This method is based on the one-time pad, or OTP, which was very popular during World War II. OTP uses a symmetric encryption key that should be as long or even longer than the data being encrypted. For example, if you had a small message that was only 15 bits long, a random 15-bit key would need to be generated. That key can then be used to encrypt your message using a process called exclusive ORing, or XORing. XORing means that we compare two strings, our message and our random key, to generate an output. We do this by lining them both up. If the bits match, a 0 is generated. If they don't match, a 1 is generated. The output is our ciphertext. What makes this so interesting is that this demonstrates perfect secrecy. This means that to a hacker, this ciphertext looks completely random. It would be just as difficult to brute force the key as it would be to brute force the data itself. OTP only works properly if our secret key is only used once. If we use it more than once, a hacker could then start to decode the secret key. OTP works great if we're dealing with small messages, but what if we needed to encrypt every video? A video can range from 500 megabytes to up to 5 gigs or more. Since every video file would need to generate a key that's the same size or larger than the video, we would quickly end up running out of hard drive space. So with today's data types, the one-time pad just isn't very practical. Stream ciphers offer a solution to this problem. A stream cipher can use a smaller fixed-length key that can be used repeatedly throughout the encryption process. This key is called a seed key, and in our example, we'll say that it's 2048 bits. This key is run through a pseudo-random number generator, which outputs a new and unique encryption key called a key stream. Notice that this new key matches the size of our data. The key stream is then XORed with the data to give us our ciphertext. Many symmetric encryption algorithms use the block cipher method. Block ciphers, instead of encrypting our data one bit at a time, the data is encrypted one chunk or block at a time. The common block sizes used are 64, 128, or 256 bits in length. For example, let's say that we want to encrypt a file that's 800 bits in size. Using a 256-bit block size, the data will be encrypted 256 bits, or 32 bytes at a time, until the process is complete. Since the last block ends up being smaller than 256 bits, the algorithm pads the block with some random data to bring it up to 256 bits. As shown here, there are several block cipher operation modes that can be utilized depending on the application or use. Let's talk about a few of them. Electronic Codebook mode, or ECB, is the simplest block cipher operation mode. With this mode, each block of plaintext data is encrypted separately. Several blocks can be encrypted at the same time, allowing for faster encryption. The biggest disadvantage is that identical data results in the same ciphertext, meaning that a hacker would be able to decipher some of the data if they intercept multiple blocks. Cipher block chaining is like ECB, except that it uses an initialization vector. The initialization vector is a starting variable that's XORed with the current block's plaintext to encrypt the data. The first initialization vector is a random string, and each subsequent initialization vector is the ciphertext from the previous block. CBC is more secure than ECB, but slower because multiple blocks can't be encrypted at the same time. Cipher Feedback mode, or CFB, also utilizes an initialization vector, but instead of using it on the plaintext, the initialization vector is encrypted, and then that result is XORed with the plaintext to create the ciphertext block. Now, this is the equivalent of encrypting the plaintext with a one-time pad. Output Feedback mode, or OFB, is practically identical to Cipher Feedback mode. The difference is the initialization vector used after the first round of encryption. The CFB's output is XORed with the plaintext, and the result is the next block's initialization vector. The process is the same in Output Feedback mode, except that the encryption's output is the next block's initialization vector before it's XORed with the plaintext. Next, we have Counter mode. Similar to ECB, every encryption process in counter mode is separate. Instead of using an initialization vector, counter mode uses a nonce combined with an encrypted counter. Nonce is simply a fancy word for a random string that's used for all blocks. The nonce's encrypted output and counter are then XORed with the plain text to create the ciphertext. The counter starts at 0 and increments every block. By combining the nonce and counter, each block is using a different value so that even if the data is the same, the output will be different. If we want to provide authentication with confidentiality, we can use the Galois counter mode, or GCM. This mode works just like counter mode. First, we have the counter and nonce encrypted. The output is XORed with the plain text to give us the ciphertext. Now here's where things get different. The ciphertext is combined with a special hash. That output contains the ciphertext along with a message authentication code that gives us assurance that the data hasn't been tampered with. Because this method is efficient and provides authentication, we see it used often with network communications, such as wireless networks and web servers that use SSH or TLS. We're putting more and more Internet of Things or IoT devices into our networks. The need to encrypt data has never been more important. In 2018, the National Institute of Standards and Technology, or NIST, began the process of standardizing encryption algorithms called lightweight cryptography for these types of devices. Many IoT devices are small, low-powered devices that don't have the resources to handle the encryption methods we've covered. IoT devices have limitations such as only having a small amount of RAM and CPU power. Some devices even run on batteries. Lightweight cryptography algorithms must take this into account and still provide high levels of security while being efficient. One huge risk with all encryption is that the data must first be decrypted before it can be used. Homomorphic encryption addresses this concern by allowing encrypted data to be used without decrypting it first. This is done by performing mathematical operations on the ciphertext instead of on the actual data itself. Homomorphic encryption works like other asymmetric encryption methods by using a public key to encrypt the data and a private key to decrypt it. It helps to look at data as math problems to better understand the differences in the types of homomorphic encryption. There are 3 types of homomorphic encryption. Partially homomorphic, which allows for only simple mathematical operations like addition and subtraction to be performed. Somewhat homomorphic, which allows for more complex math, such as multiplication to occur, but only for a limited number of times. And fully homomorphic, which can handle any mathematical operation an unlimited number of times. Homomorphic encryption has the potential to be a game changer, but as of now, it's incredibly slow and inefficient. That's it for this lesson. In this lesson, we looked at the different ciphers used in cryptography. We first examined the stream cipher, which encrypts data 1 bit at a time. Then we looked at how block ciphers work and the different operation modes. Finally, we looked at 2 newer forms of cryptography. Lightweight cryptography is being designed for IoT devices, and homomorphic encryption allows data to be used without having to decrypt it.